All right, there we go. So we're going to walk through some fundamental principles of polymer structures, how they're made. So this is going to really kind of push your understanding of the way that polymers work, the way that we use them, all of those sorts of things. These are really, really important for how how they behave, how they can be used in different applications, like say the materials selection project that you're also working on. So polymers is a combination of words, just meaning that it has many units repeated. So depending on what the chemical makeup is of, in many cases, a two-carbon chain. It's not always a two-carbon chain, but it's, for the sake of thinking simply, common examples are polyethylene, polyvinyl chloride, polypropylene. Um, Polyethylene is used in a lot of different plastics and things for um, things that are not considered to be completely dishwasher safe. Polypropylene is what most containers for food are made from, a very large majority of them. Polypropylene is the plastic that allows for hinges when it's really, really thinly injection molded. Does really, really well making hinges. It's very resistant to food, heat, all sorts of things. Not very resistant to UV. UV really does a number on it. Polyvinyl chloride, those carbon chlorine bonds, a little stronger, a little more resistant to UV for longer. But PVC is used in a lot of back-end mechanics of delivery. Plumbing especially is a good example where that's used, but also PVC piping for even things like soft drinks at a restaurant or something of that nature, right? A lot of different examples of those. So it has a chlorine added onto this carbon backbone, and so it's every other one because it's a repeat unit. So you can have a lot of them, you can have not very many of them, depending on what you're trying to make and for what application. There are also a lot of natural polymers. Wood, we've talked a little bit about that. We've talked about how people are starting to try and hybridize wood and synthetic polymers to make hybrids. Those materials are actually kind of interesting for a wide range of reasons. Rubbers, anything like all those nitrile exam gloves, right, that become an interface between you and yucky things. Cotton, wool are other examples. The nitrile rubber is not really a natural type, but similar. Leather is a type of polymer. It's a bunch of cellular material that has been dried out and sort of, in a sense, frozen in a specific state. So it's a really kind of an interesting material. Silk is another good example. We weave silk threads into things, but it is a naturally made polymer. So there's a lot of interesting things that we can do with those. The oldest known issues, or the oldest known uses rather, is, you can tell I've been grading tests for too long if everything looks like issues. Rubber balls that the Incas used. They had a really fun and exciting death sport where you had to hit the ball into, it was kind of like basketball, but with no hands. And at the end, they killed the losing team, or maybe they killed the winner. Can't remember which, but either way, people died. So it was way better than basketball, 100%. Noah also used a natural polymer called pitch for the arc. So that's a naturally occurring tar-like substance. And if you've ever dealt with something like parking under a tree and getting tree sap on your car, you know that some of these natural polymers can be pretty obnoxious to remove. So that would be a good waterproofing agent were one to build a boat without having lots of sophisticated tools and things available. Meanwhile, he was probably a better craftsman than most of the craftsmen of today, but that's a different story for another lecture. So composition-wise, there's a lot that's going on here. Most of the hydrocarbons themselves are going to be carbon hydrogen. Sometimes there's a substitution. So the core backbone of a very large number of polymers is ethane. Once you change some of these things, you change the number of bonds, you change the way that these materials behave. But starting with ethane, there's a few principles that we're going to cover that are helpful to understand in terms of why polymers do what they do and what it means to have things like degrees of freedom stored up in a polymer. So what exactly is that? That's something that you'll get a better appreciation for today. So single bonded carbon, 3 hydrogens on either side is ethane. And that's a saturated hydrocarbon. So this is at the highest stored energy state in terms of heats of formation. This is why we use ethane, methane, and propane as fuels. They are starting out at an energetically high point. They, with just a little bit of incentivization, release those hydrogens and break the carbon-carbon bonds, which are the really high energy ones. And those breaking of the carbon-carbon bonds is what we get out in terms of heat from the flame in the gas. That's the actual heat energy, is primarily those carbon-carbon bonds. The carbon hydrogens are a very small percentage comparatively. So the boiling point you can see of those, methane boils at a very, very low temperature, so it's kind of hard to capture. Some of the other ones like butane, reasonably stable at room temperature, reasonably, doesn't evaporate super fast. Propane, really, really fast. Pentane, and as you get longer in the carbon chain, so all the way up to, in this case, hexane, 6 carbons, your actual boiling point comes somewhere on your room temperature, and you'll note that these are not all gases. So after about butane, they're often found in a more liquid state, especially something like hexane. You can boil hexane, but you actually have to add a fair bit of heat. Considering that room temperature in C is about 25 C, unless of course you're in Phoenix, and it's really hard to keep the room temperatures under about 75 C some days, or so it seems. So we also have double bonds that can form. So what these do is they become they release some amount of that energy between the single carbon-carbon bonds, and then they're left with just 2 hydrogens. What that also means is now they're linked together almost like the sides of a ladder. And so twisting and turning, they lose that degree of freedom to be able to spin freely, where ethane can spin with each side freely relative to each other. The double bonds constrain that motion, and so you don't have nearly the same degree of being able to absorb energy and put it in lots of different kinds of motion, because energy is just the kinetic movement of molecules. So this is especially important in polymers because it behaves a lot differently than something like a metal does. So the double bond that's formed allows you to have ethylene. If you have I've heard it referred to as ethene some of the time, but for the most part, ethylene, keep things simple. I'm not going to beat you guys up on the final over like, if I had 3 quarts of ethene, how many watermelons does Susie have? Because I don't want to have to put in a bunch of options for short answers for that, and I won't be able to capture all of the sarcastic answers that I'll get back, right? So that would be a thing that I have to manually grade, which I'm de-incentivized to do. So something like that's probably not going to be on the exam, but something like ethylene having double bonds, or acetylene or ethene, Acetylene is typically what we're referring to it as. These are the first is the group of anes, and the second is the group of enes, and the third is the group of illenes, typically, and that's the triple bond formed. So this is also where you get carbon-carbon triple bonds. Those are highly motion constrained. So the only thing the molecules can do is sort of break apart violently, and this is why we use something like an acetylene cutting torch. But because of the way that the bond structure works, you have to there's a pretty tremendous amount of energy where you have to break 3 bonds at the same time, and that's why those acetylene cutting torches work well, because they're at high temperatures. So it creates some interesting issues that we have to overcome. So and I may have a temporary interruption coming up here at an undetermined time. This team doesn't really communicate very clearly with me, but I'll try and give you guys a heads up when that happens. So what we're talking about here is the concept of isomerization. And what isomers do is isomers allow for more degrees of freedom in something in order to have more states available. They're chemically the same formula, so same number of atoms. These are things that you've covered in chemistry, but probably long since forgotten, because everybody files chemistry under T for terrible. The different bond arrangement allows for tree-like formations, or branch-like structures. And what that does is that allows for a lot of different kinds of behaviors of the chain that still has similar properties to the others, but they're slightly different because of the way that the solution is going to solubilize something. For instance, it's a whole lot easier to imagine dropping something like a golf ball into a pot of spaghetti and it kind of working its way down. But if you tried to drop it into a pot of broccoli or something that's a lot more branched, it's going to have a tougher time working its way to the bottom, right? Something that provides a higher degree of interference. So some of the properties, although the overall boiling points will be similar, the way that they interact changes just enough for them to be classified as different things. So they're also, their name typically changes. We don't call them the same thing because that would get really confusing, and how anybody got any information out of all of that time of alchemy is sort of a little bit beyond me, because I'm still not sure how I could tell you the process of alchemy leading to what we have today as chemistry, because there's a lot of quantum leaps there in between, quite literally, actually. So a normal octane versus a dimethyl hexane, the 2 and 4, again, just commenting on the second carbon. So the chain is here in the center, and the outer branches here are the 2. So the second and the 4th carbon are the ones that have the methyl group. So dimethyl hexane, 6 carbon chain with 2 methyl groups attached. So different behavior, same molecular formula. Important to understand about polymers. What they do often is, with the right environmental conditions, they create radicals. So again, this is something that you've seen probably once briefly in chemistry previously, but it's the idea that a free radical is a free electron, and because nature abhors a vacuum, a free electron by itself is unbalanced, and that's not something that nature can tolerate very well. So free radicals only exist often for like a free radical existing for multiple milliseconds would be an eternity for a free radical. It's something that happens almost instantaneously. We know that it has to happen because reasons. In order to try and actually get through the material today, we'll try and stay focused. But what the free radicals do is they are very highly reactive species. They cannot stay in that state very long. So it is often thought of in a lot of instances as an instantaneous process. The very moment that a radical forms, it has to react, kind of thing. So it's a very, very rapid process. And what that does is, as a free radical comes in and interacts with the monomer, it immediately sets up a chain where that first group now can react with, so that first ethylene gets turned into a new species. So it has some R group. We don't have a specific name for this because it depends on what the R group is. That almost immediately reacts with one of the adjacent monomers, and this chain forms. And so it happens as a chain reaction. And this is kind of where that term comes from, is it's literally forming a chain in a reaction. So it's eating up all of those monomers to become a dimer and then a trimer and then a polymer. Once it has more than 3 units, is typically referred to as a true polymer. So the initiator can be all different sorts of things. One of the examples that they use is benzoyl peroxide. Anybody offhand know where that compound is used most often? Anyone? Bueller. No? I don't see anyone hazarding a guess. There we go. I figured there was a possibility one of the girls might have actually read the label of all of those bottles they've got. Benzoyl peroxide is a facial cleanser. This is the compound that, because of its free radical formation, it likes to do all sorts of things, including the mechanisms that allow it to be able to dry out skin. Because it has these 2 oxygen bonds, and oxygen-oxygen single bonds are rather unstable comparatively, because oxygen loves to run around and change bond types. The free radicals that it forms react very quickly and repolymerize things. So there's a lot that goes into that. But that's a good example of an initiator that can start a reaction. So there's ways to remove initiators and things later on, but the key is you want something that can act like a highly charged reactive species and easily form a reaction. So hydrogen peroxide, same kind of example, where you have an oxygen-oxygen bond that you're trying to break. And so it's H2O2. So instead of these double bonded rings, what you've got is just a hydrogen over here. It's the same kind of idea. The reason it's reactive, and it's more aggressively reactive than benzoyl peroxide, is these benz rings slow down the process. There's more mass involved. The kinetic energies are a little different. The stereochemical hindrance is different, and some other factors. But what those do is those start the reaction that you're watching. So polyethylene is a good example of the kind of the most simple, basic polymer. We use it all the time. It's fairly inexpensive to form compared to other polymers. So this is the reason why it's used so often in so many cases. but it's not highly temperature tolerant, doesn't have good UV tolerance. It degrades quickly in outdoor environments. Not very chemically resistant overall, because there's a lot of ways that this can react. So good and cheap, but not an all-purpose polymer. But what it is typically a very long chain. So the difference here, for instance, between a long polyethylene and a paraffin wax is the number of the length of the chains, basically. So waxes are within a range of carbon lengths. They're typically going to be under about maybe 20 carbon length. They're going to be often much, much shorter than that, probably closer to 12 in many cases. So there is a little bit of give and take to a degree there, but the general rule of thumb is really long polymers are not going to work in applications where you need something that is a waxy substance. You need something that can melt apart and separate. So there's not much cross bonding, or what we're going to learn is cross linking here later, because that's another type of interaction that we do with polymers to stitch the chains together into something that we'll recognize as truly a network, a net-like shape of these chains. So the polyethylene has the simple repeat unit that's carbon, 2 hydrogens, another carbon, 2 hydrogens, always, forever, for all of time. PVC, polyvinyl chloride, has chlorides, has chlorine attached in place of one of those hydrogens. PTFE, Teflon, is the trade name you'll recognize that as. Polytetrafluoroethylene. What that does is that allows for all of those hydrogens to be completely substituted with fluorines. What that does is really prevents these materials from reacting with really much of anything, because these fluorine and chlorine, to a little bit lesser degree, is not really interested in a lot of interactions. This is why once it's reacted from something like the super dangerous hydrofluoric acid, it's perfectly happy to donate that proton. So it's a really mean, aggressive kind of acid. Once it's reacted, and sometimes that is used in the process chemistry of making PTFE. Once it's reacted, it's a lot of energy to unreact it, and this is why it's temperature tolerant for heat cycling and things on cookware. But if you have nonstick cookware and you can see, shiny metal at the bottom and lots of deep scratches, you've probably eaten the majority of the actual Teflon layer. You probably want to get a new pan. Maybe invest in a ceramic one that's not going to degrade to the same degree. Some good life advice there. Polypropylene is very commonly used in other applications. So this is higher temp applications where something needs to be dishwasher safe or be autoclave safe, for a lot of medical equipment and things like that. So polypropylene is used a lot of times there. The downsides for it is polypropylene is not as easily machinable, and it has some other limitations of that variety. It's fairly slick, a lot like the PTFE, because of all of these methyl groups are much more hydrophobic, so shedding of water, than the hydrogens are. So kind of hard to machine, kind of hard to work with, good for injection molding, difficult for other processes. So these are some of the things that we need to know in terms of what the units look like. So there might be an example where you have to match those or something like that, where that'll get you some of the information. Polystyrene, think styrofoam, polystyrene. These are really usable for insulating things. Those Benz rings make them relatively unreactive. There are ways to dissolve it, definitely, but they're fairly stable, especially once they're turned into something else. The polymethyl methacrylate, PMMA, is another commonly used material. So there's a lot of mechanical things that we use PMMA for in not as much the food space, but sometimes there's some other examples. And Bakelite, a little bit less common overall, but there are a couple instances where this will be used. So we'll get into some more of the applications here later. And I'm about to have that interruption that I spoke about. Also, the polymers here, we'll touch on this when I get back. So let me take care of this real quick. All right, my apologies. A couple more. There are some applications for a couple of these that you guys will remember. So nylon 6,6, polyhexamethylene adaptamide or adipamide is commonly used for any kind of nylon clothing. Most of your backpacks are going to be a variation of nylon 6,6 in different weaves. Even I think some of the ballistic nylons are going to be nylon 6,6 as well. So this is more akin to a because it's an amide. What that means is this carbon nitrogen pairing. So there are, in this particular case, you have you're always going to have a double bond oxygen and then some kind of R group coming off of it, but you've got a double bond oxygen, nitrogen, and then you've got you've got one type of unit and you've got another type of unit, and the 6,6 is the 6 carbons here plus the carbon here, the 4 in this chain. So that's what this means. It's repeated and this many. So if you were asked something like, how many carbons does this particular polymer have? 6 plus 6 is 12 in total. There's also nylon 12. That particular one is much more durable in terms of temperatures and autoclave performance. So things at high temperature and pressure, those polymers retain their shape. So think of something like, for instance, a Nalgene bottle is going to be kind of more in that category. So the reason they became as popular as they did, as quickly as they did, is they were, instead of using acrylic polymers that would break on impact, they were using nylon that was much more durable and much harder to break. than some of these other things. So polyethylene terephthalate is another one. So PET, this is a polyester, an ester being one of these groups that has, again, these double bonded oxygens. What these do is these allow for, and this is the whole repeat unit for this polymer. So what these do is they allow for common drinking containers, molds for different kinds of candies and lollipops. A lot of times can be made in PET. A lot of plastic bottles of all varieties and sorts, sauce containers. Probably all of your lives, you've only ever eaten ketchup out of a polyester, a polyethylene terephthalate bottle, if I were to guess. So there's a lot of applications where this is used. It's also used very heavily. A glycolated form of this polymer is used in 3D printing very commonly for being a low odor but fairly temperature tolerant polymer for what they can do. This polycarbonate, PC, is another material we use very often. So polycarbonate and acrylics have some kinds of similar behaviors. They tend to be very, very, very hard, very stiff. And a lot of that has to do with the fact that there are so many of these chains that have the Benz rings in them. So those Benz rings tend not to want to flex because the circle inside, remember, means that they have a double bond all the way around. So technically that double bond sort of has to move around the ring, but we won't go into that kind of gory detail for this. Just know that the double bonded rings do not wish to bend and flex at all. They are very, very stiff the way that they behave. So because of that, these materials don't flop around and twist and turn and do all sorts of unusual things like the nylon can do. The nylon has mostly single bonds with everything, so it can flip around and move and flex and twist chemically, and that's why the bigger, bulky properties are similar to that for nylons and why they're used in so many applications. So the polycarbonate is sometimes even used in dishware and things of that nature. It can handle some higher temperatures. It has to be made and manipulated at higher temperatures, but that's something that you guys are not going to encounter probably often for end use, just for a range of reasons. If anyone cares, there is a three-dimensional viewer app where you can rotate these in 3D. This was like a really fun and exciting thing in the 90s when I was a kid, and 3D was not really a thing yet. They hadn't invented the third dimension. So now, with all of you guys having all sorts of crazy, silly, immersive video games and all the frames and things, you're like, wow, what a crappy image. But at one point in time, this publisher was really, really proud of this resource. Like, this was a big deal. You just don't understand how big a deal it was that you could move the molecule around in 3 dimensions. Molecular weight is a really important property for what we did, or for what we do with the polymers. So low molecular weight simply means short chain. Higher molecular weight means longer chain. It's really simple, really straightforward. They're often different lengths. There's often a distribution of molecular weights because sometimes it's very hard to control the reaction precisely, and 2 chains that are being made near each other might be competing for resources, and one might be growing at a little faster rate than another one in the same area. unless the system is really thoroughly well mixed, especially because some of these solutions, as the polymers get longer, the solutions become more and more viscous. They become harder and harder to mix. They take more and more energy to be able to do that. So there's a lot that goes into this. But what we can really focus in on is that these are all of different kinds of molecular weights. They need to be, because of the way that the chemical reactions work, they can't all be the same. There are ways to control and constrain what the average molecular weights are, but the total number of molecules on a whole is going to be a fixed number, and that's based on just the molar ratios. There's conversion efficiencies and some other things that play around in there, but the average number and then weighted average are very different. So we'll take a look a little bit more closely using a data set for this. What we can do is we can take the mean, and then we can also use the weight fractions, or basically so we can take a weighted average, and then we can take the numerical average. So the numerical average and the weighted average in a given population of polymers might actually be very close, or close enough as to be nearly the same. That would be a fairly, what's called monodisperse, so not highly dispersed polymer population. If it varies widely and those two numbers are largely different, then it's a polydisperse, or many different ranges of dispersity. That makes it much more difficult to accurately predict the properties. But if you're making something like, think about another common polymer, anybody that's ever used hot glue, right? Sometimes you'll get a batch of hot glue that seems to really stick to stuff very, very well. And sometimes you'll get a batch of hot glue that you're not sure could stick to itself, let alone anything else. So it might be an entertaining project for you guys to try at some point, and see if you could hot glue two hot glue sticks together. So I'm told it's possible. The weight fractions are going to be important for a couple different reasons. They're used as really the main thing that you can measure easily. So I'll give you a little bit of kind of quick context for this. What the weight fractions do is they allow us to separate out by effective size through a process called dialysis. So we take a sample of something, we dilute it down in water, and then we measure something like an optical interference measurement. So refractive index of the water, or something like that. We send some sort of beam of light through the water, measure something about it, intensity, scatter, angles, whatever it is, and we let that membrane that has pores of a certain size range, we let things exchange across that membrane over the course of time, and then measure the changes in what the refractive index is in that starting solution. And the things that are small enough to go through that membrane and be solubilized on the outside, those are going to be reducing the optical density, the refractive index, all sorts of things of the solution itself. Then we have some sort of an idea, based on the amount of time, based on what size range that particular membrane was for excluding things. We have some kind of an idea what the percentage or average molecular weight of something might be. There's some other mechanisms that we can use to tell that as well. But if we had a population of student masses that looked something like this, right? ranging from 104 to 380 pounds based on, first, the number fraction for the students, then second, the weight fraction of the students. What actually, what weights do we get back out of those? So the way this calculation looks is you start with ranges of about 40 pounds. So 80 to 120, 120 to 160, and so on. And what you do is you take this and you calculate a weighted average, meaning the number times the weight itself. So in this case, the number, so 2 instances of 110, 2 instances of 142 for the mean of that range, right? Because 110 is equally between 80 and 120, at least for this data set. Similar, 140 is actually in the middle there, but because it should be technically 100 if they were using the true mean weight out of those. So I think their starting data point is biased there, but the midpoint of those ranges are chosen specifically so that the weights within those ranges allow for a couple weights that are adjacent to be used similarly in the data set. So it averages out the way that we see here. So in that 80 to 120 pound range, we've only got 2 out of the 10 total, and so that's 0.2, and our weight fraction for that. So the weight range versus the number range, the weight range would say 2 times 110, the actual weight itself, because it's the second formula there, the N times W over sum of the NWs, divided by the sum of the NWs, which is 1881. So we have 0.117 instead of 0.2. So that suggests the weight calculation suggests a different range. So what that formula looks like for the number versus weight fraction averages, we determine each of those weight fractions through the same kind of calculation, and then we multiply those through by the actual weights, the masses. And then that gives us our end value. So 188 would be the numerical weighting. The weighted average for the weight fraction calculations for the whole population would be 218. So a significant difference between those two methods. The reason this is important to know is a polymer that's closer to an average of 150 chain length versus a polymer that's closer to almost 250 average chain length. Those two things behave wildly differently for a given application. So we need to understand why this weighting calculation is important, and that's really what it comes down to. Is what these allow us to do is they allow us to understand, especially when we're mixing different polymer types in the way that we might be for tuning specific properties, that gives us some flexibility and some range to work with later. And you'll see kind of why it's important, because it changes some of the properties and how they operate. So I think we've got enough time that we should be able to get through it. So I'm going to do my best here. And then that'll put us on pace for success as we close the semester. Degree of polymerization is an average molecular weight divided by the mass. So that's the molecular weight of the repeat unit. So with a degree of polymerization of 6 here, this would be 12 total carbons, and the repeat unit itself as the 2 here, 12 divided by 2 is where they're getting 6 from. This is important for copolymers, and what copolymers are just exactly what they sound like. Think of it as you're making I guess there's a few different ways to think about the process, but you're trying to get something like a Teflon-like water repellent function to the polymer. So one unit or one block is going to be hydrophobic or afraid of water. You have another one that is performing some kind of a function, like we're going to see when we look at the organization of polymers. You want it to make something like a bubble or a sphere. So you want it to interact with itself and be maybe in that case, you want it to be hydrophilic, meaning loving water, so that it'll capture a thin water layer around the inside and form something like a bubble or a sphere. And then on the inside, maybe you need to do other stuff that is also fundamentally hydrophobic. So you have a third block that's going to be hydrophobic. And the goal is to try and get it to assemble itself in a way that the two ends stick out, the two hydrophobic ends stick out from the chain, and the hydrophilic middle grabs onto a water layer to form a bubble. So there's also, for the case of the copolymers, we introduced this variable called the chain fraction to specify, hey, how much, what percentage is this particular repeat unit, and that way we can keep track of all of the accounting for it. So we have linear arrangements where some peptides and things naturally do this in the body. A lot of longer chains of amino acids, small peptides, are going to have something like sulfur-sulfur bonding that's very much like that. So kind of weak secondary bonding that's represented in the light blue. Then you have this branched arrangement, and the branched arrangement allows for some of these smaller chains to come off of the sides. You have cross-linked, meaning these kind of network-like relationships where it creates almost truly a net of the polymer itself. Cross-linking happens to form all kinds of gels. Anyone familiar with calcium alginate by chance? By the time we're done with today, some of you are never going to eat ever again. Calcium alginate is used in a lot of foods. Specifically, if you leave something like a block of Velveeta on the counter and you just let it sit there, basically nothing happens to it. That's because it is a polymer. It is a cross-linked alginate gel, and so it's an algae derivative that they turn into a network by this cross-linking process, by this ion exchange is what's done there, and that cross-links or builds bridges between these chains and creates the gelatinous network that is Velveeta cheese. It's in a lot of other foods too, but anytime you have something like stadium nachos or something called processed cheese food, good chance that it has some calcium alginate. That's also why you have to heat it up in order to get it moving and flowing, because it wants to stay still. But even at highly elevated temperatures, it's not just pouring and liquidy, it's going to stick to your chip. So the degree of cross-linking actually becomes very important, because if it's too highly cross-linked, then it doesn't melt properly and behave like we would expect nacho cheese to. So if calcium alginate were only a slight percent different, we could never have nacho cheese. So that would be pretty sad. But these networks, what they do is they allow for changes in conformation. They allow for stretch, and so bonds can rotate, they can stretch, they can compress, they can break, and they can form. That's all they can do. But a lot of energy is stored up in the molecule moving around in different conformations. That's where a lot of the energy of these materials is stored. So for this, there's a couple examples drawn here. Basically, with a single chain, they can rotate and do all sorts of things. They can do a hula hoop around each other, and all of these bending and twisting modes are available to the long single bond chains. Once you start disrupting those with other R groups, with double bonds, with other things, you lose some of those constraints, or you pick up some constraints, you lose some of that freedom, some of the degrees of freedom for the molecules themselves. And it becomes very hard to break apart those molecules. So they behave very differently from metals, in that metals are not trying to do this. They're not trying to rearrange their shape in order to take an impact, or in order to take lots of thermal energy. So hugely different kind of behavior from the metals we've been studying. And that's why it's important to go over these as well. So you don't have to break these bonds for single chains, single bond chains. You don't have to break the bonds in order to have them move into all these different weird conformations, making snake shapes and things. And this is what molecules actually do at a small scale. So another factor that is also used in a couple things is the chain end-to-end distance. And depending on how it's used, the chain end-to-end distance, what that does is it tells you some information about how much the coiled polymer has to sort of stay away from itself in order to exist in a semi-stable state. So this would be considered a semi-stable state, where it's not necessarily trying to react, it's not necessarily polymerizing farther, but you get some information about the way that these behave. So that's what they're talking about the chain end-to-end distance. At the end of the long, gnarly spaghetti chain, how far apart are the ends? And that can tell you something about how the whole will behave. Other configurations mean you have to break bonds. So conformations, really important distinction. Conformations, 100% guarantee some of you will get this wrong on the test. Conformations are these bending, twisting arrangements. So these are available states for the molecule to be in. Literal positions for the molecule to be in. Configurations rearrange bonds. So this has to do with something called stereochemistry. So if you did something like this top example and you rotated the second carbon bond, you would have the R on the other side. So those two are the same thing. Meanwhile, if you had a stereoisomer, they're a mirror image, but you can't superimpose. It's not the same molecule, just rotated somehow. You have to break bonds to be able to make it look like the first one. So across some mirror plane, you'll see some commonality, and that tells you something that it's often a stereoisomer. Tacticity is used as a term. It's one that's important for the arrangement of molecules along this chain. So isotactic is all the ducks in a row. So iso is all ducks in a row. Syndiotactic is chaos. It's alternating sides. It's not truly random, but it is alternating sides. Truly random is a different discussion for a different day. One where everybody's had sufficient caffeine. But this is one of the things that we can understand about the terms that are being used if we have a clear idea of what is iso and what is syndio. Iso meaning same side and syndio meaning opposite sides or opposing sides. So when the chain becomes three-dimensional, because they don't just play nice and lay flat on a piece of paper, in real life they're moving, changing, they are contorting, so they are changing specifically conformation all the time whenever they can. They're not always trying to change the they're not always trying to change the chemical bond arrangement. So yeah, this one. So atactic is chaos. That one should be pretty easy to remember because that's about the sensation that you guys feel as soon as you're dropped into any kind of an online exam. So atactic is the chaotic one. It's unpredictable, unreliable. There is no pattern. And then here's some very overused words in today's environment, but they actually have specific meaning. They're not what they have been used for in recent years. Cis meaning same side, trans meaning opposite side. The cis isoprene means the carbon in the methyl group and the hydrogen on that second double bonded carbon in the backbone are on the same side. If we rotate that and change the conformation, which can happen, then it becomes trans, and you can play around with some live model examples, but if you were to try and put a cis and trans, basically those images over top of each other, what you would have is you would have an inability to make them match up. They're not the same molecule. Sometimes there are advantages to the natural properties of a cis polymer. Sometimes the trans is preferable for certain features and behaviors. So there's a little dependence on what the end application is, whether or not these are useful. So when everyone's talking about the great low fat versus high fat debates and all of the dietary things that have gone into that for decades, cis and trans in that context mean that you're going to have some examples where it's cis. Pretty uncommonly when you hydrogenate these oils, so long chain oils, they have a bunch of CH3s on them. They bubble hydrogen through these solutions of oils, and it displaces some of those, chemically leaving behind a bunch of hydrogens. That's hydrogenated oil is what this is. So it's forming of a polymer by adding a high volume of hydrogen, and whether it goes on the same side or opposite sides is kind of dependent on reaction conditions and some random probabilities. So it's awfully hard to control. But the trans fats have these methyl groups and hydrogens alternating, just like what you see on the right side. The cis fats have the hydrogens all substituted on the same side, and they're said to be better because, again, reasons. Copolymers turn out to be incredibly important for a lot of reasons, and there's a range of them in use. And what those can do for us is we can alternate them. We can do actual blocks, which are pretty common. We can also do grafts. So depending on what we're trying to do, if we're experimenting with something, sometimes we try random walk polymers. If we are looking for a mix of properties, we often do something alternating. Blocks are for specific kinds of functions in different regions of the polymer to behave more like some biological entities like proteins or lipids in membrane spaces in the cells. So these polymers can do lots of different kinds of things. Maybe one is UV tolerant, the other is some other property, and the last one is you want it to be easily water soluble so that it can come off the surface without adhering very strongly or something like that. So the random can be useful, but it's no rhyme or reason. It's pretty chaotic. Alternating is very straightforward. Grafting is also a common technique. This is where we want some properties of two different things, but we don't want to polymerize them together in the same chain, partly because we may want them to interact with other things and be a reactive species. So something like a ceramic coating is going to start looking at a behavior like this, a graft type polymer, and the particulars become sort of that intellectual property to be able to understand what you're working with. But that leads to this process called crystallinity. So crystallinity, what this does is this has a region of polymers that behaves differently from the rest. They sort of organize themselves in terms of bond arrangement, hydrogen bonding, all of these things. They rearrange in such a way that they become sort of tightly packed and sort of constrained in some of their motion in this cell. So this is a polyethylene unit cell. What you can have happen is these regions, for instance, maybe these outer loops are all hydrophilic. The inner loops might be hydrophilic, they might be hydrophobic, it depends. And the middle layer, which is the folded chain structures. So this is some kind of a long polymer chain or a series of long polymer chains that are folded in such a way that the parts that we like the properties of are exposed to this liquid environment. Likewise on the inside, but this center region can be crystalline in behavior. So what does that actually look like in practice? The polymers are rarely all 100% crystalline. There are usually regions. Then there are other regions that are called amorphous, meaning without morphology or without clearly organized structure. This is something that becomes pretty important to understand. And the degree of crystallinity is typically expressed as a percentage. So like a simple ratio of amorphous to crystalline regions gives you some very different sorts of results there. So yeah, the heat treatment can be done on these polymers. It's not the same process as with metals, but it's carries over some of the same kinds of principles. In this case, trying to allow chains to stretch out and reform and change the conditions to usually increase the crystallinity, because in polymers it's desirous typically for them to become more stiff rather than less stiff, because their downfall and weakness is often that they are too pliable, they are too ductile, they are not brittle in their behavior, and more importantly than brittle, they're not typically overly stiff. So this is an example of what this can look like. Some of these multi-layered crystals, single crystals can also form under carefully controlled growth rates. So this is something that was taken from GE from years ago, growing a crystal with polymer. So there's also semi-crystalline polymers that have something referred to as a spherulite. So you have some kind of nucleation site, typically not going to be a perfect sphere. In fact, very often not going to be. So there's amorphous material in between the directed spherulite growth. These are kind of some representatives of what those regions might look like. It's a little bit hard to visualize exactly what this means and what it would be like. So I did find an example they show you here. It's really hard to tell much from that image. So I thought this one was a lot better, where you see the idea of a chain being folded in and out millions and millions of times, because they can be very, very, very long, or connecting with other polymers that have similar properties, and they all collectively form something like this, called the spherulite region. So there's a way to understand it and make sense of it, to make it all sort of work. It's a lot of material, so I know most of you probably didn't catch all of that. Hopefully you'll get a chance to go back and rewatch part of it. If I pull together some videos for the Monday section that will help kind of add clarification, I will post those for you guys, because there's a lot of material there. There's a lot of different areas that I could ask questions. Most of them are going to be concept questions. So you'll want to study this chapter broadly and kind of go through the homework, make sure you understand what kinds of questions we're asking. And that way we can make sure that as this gets incorporated into the final, you guys are not going to be left high and dry. So let's see if you guys can beat the average watch time of something like 9 minutes that I think I've had on some of the other videos, and see if you can make use of more of it or not. So I'll stop the recording there, but any questions for you guys? Because I know we're going to run short on time here.